Hello students, this is Professor Chalai, and in this video we're going to look at standard enthalpy of combustion. As always, you can follow along with our Chapter 5 workbook. By the end of this video, you should be able to define what a standard state is, or what the standard states are, and then use the standard enthalpy of combustion values in calculations. Okay, let's get started. So far in the semester, throughout this course, we've talked about enthalpy lots of times before. We talked about what a combustion reaction is. Something is burning in the presence of oxygen to produce other things. So before we can figure out what a standard enthalpy of combustion is, we then need to figure out what we mean by standard. And standard here just refers to what we call the standard state. And so all of these reactions, what we perform, they actually depend on what, other conditions like the concentration of the material or the temperature that it's happening at. And so standard state here just means that it's a set of common conditions that scientists across the world have agreed to use for these sorts of reactions so that we can easily reference them, so that we don't have to keep saying, oh, this reaction was done at X degrees Celsius, at 1 atmosphere pressure or all that. So standard state then is just a set of common conditions that reactions are carried out under. And we usually represent these sets of standard conditions with a little degree symbol that you see here. So anytime you see that degree symbol, it means that that value was obtained when we were under standard conditions. And so what are those standard conditions? Well, for concentration, the standard condition is 1 molar, a concentration of 1 molar solution. For pressure, people sometimes use 1 bar or 1 atmosphere. 1 bar and 1 atmosphere are different. They're not quite the same. But oftentimes some scientists might use 1 bar, some scientists might use 1 atmosphere. This is actually one of the situations where we should probably really standardize what we mean by standard states. So that's for concentration, that's for pressure. What else do we have? Temperature. So for temperature, typically we mean 0 degrees Celsius, which in Kelvin is 290. Not 0 degrees Celsius, sorry, 25 degrees Celsius. There we go. 25 degrees Celsius, which is 293.15 Kelvin. So those are our standard temperature. I'm trying to remember if there are others that I need to think of. Nope. If we're dealing with a solution, standard conditions means it's 1 molar solution. If we need pressure, standard conditions means it's 1 bar or 1 atmosphere of pressure. For temperature, it's 25 degrees Celsius as standard pressure. Okay, so let's look now that we know what standard states are, let's look at the standard enthalpy of combustion. So the standard enthalpy of combustion is simply the heat produced when 1 mole of reactant combusts. So remember, combust just means reacting with oxygen to produce, not to produce anything, combust, which is reacting with oxygen. And usually there's enough oxygen, so oxygen is not the limiting reagent. We're reacting 1 mole of the other interesting reactant under standard conditions, meaning that the temperature is going to be 25 degrees Celsius, the pressure is going to be 1 atmosphere of pressure. If there's a concentration that's needed, it's going to be 1 molar solution. Okay, so that's the standard enthalpy of combustion. It's the heat produced when 1 mole of reactant combusts, reacting with oxygen under a standard condition. So we know that enthalpy change is usually written in kilojoules, but because it's for 1 mole of reactant, we'll usually write it kilojoules per mole, 1 mole of reactant. So here's a table of standard molar enthalpies of combustion for a number of reactants that might combust, note that the equations for each of these has 1 mole of all of the reactants. So if it's carbon, it's 1 mole of carbon. If it's hydrogen, 1 mole of hydrogen, and so on and so forth. And so to balance the equation, we use however many moles of oxygen we need to use to balance this. So for example, if we're reacting 1 mole of carbon, we only need 1 mole of oxygen gas. For hydrogen, we need actually half a mole of oxygen gas to produce water, right? Because half of 2 oxygens will give us 1 oxygen. There's a typo in these. The division sign for some reason didn't pop up, so that's half a mole of oxygen for those. This is 5 over 2 moles of oxygen there, 3 over 2, and 25 over 2. Just make those corrections in the handout that you have. So here are a whole bunch of different standard enthalpy of combustion values, and here are those standard enthalpy in kilojoules per mole, not just kilojoules, because the mole here is the 1 mole of carbon or the 1 mole of hydrogen or the 1 mole of magnesium. It's specifically for that reactant. So if we burn any of these, this is the amount of energy we can expect when we burn 1 mole of them. So let's use these in calculations. Since they're all technically more standard, they're all enthalpy change calculations, which we've done quite a bit of examples for at this point. You should be able to do these. So pause the video and try numbers 25 and 26 on your own, and then unpause the video and I will go over them with you. Okay, let's get started for number 25. We're assuming that the standard enthalpy of combustion of gasoline is the same as isooctane. Isooctane in the table is right there. Okay, so what amount of heat will produce when we burn 1 liter of gasoline? We know the density of isooctane as 0.692 grams per mil. So if 1 mole of isooctane, when it burns, produces this amount of heat, how many then will this amount of gasoline produce? Is essentially what the question is asking us for. So we need to find how many moles of isooctane are we actually burning. To find number of moles, we can convert from mass to number of moles using the molar mass, right? But we don't have the mass of gasoline, we have the volume. But we can convert from volume to mass using the density, which is given. So let's do that. Number of moles of isooctane. We know we have 1 liter. We can convert liters to mass using the density, but this needs to be in milliliters first. So we know that 1 liter is 1,000 milliliter. So this gives us the volume in milliliters, and then we can now use the density to convert to mass, 0.692 grams per milliliter, so milliliters cancel out. But we're trying to find the moles of isooctane, so we just need to divide by the molar mass, which again, I'm not going to show you how I figured this out because we should be pros at this by now, but it's 114.23 grams per mole. So this will give us the number of moles of isooctane, which comes out to be 8.42 moles. So if we burn 1 mole of isooctane, we get this amount of heat. So our standard enthalpy of combustion, right? Standard enthalpy of combustion was minus 15461 kilojoules per mole of isooctane, but we actually used 8.42 moles of isooctane. So then the amount of heat that we actually produced would be minus 5461 kilojoules times 8.42 moles, which will give us 4.60 to 3 sig figs by 10 to the 4 kilojoules of heat. Right? This is negative for its heat produced, because there's a negative sign right there. And just as a reminder that it's an exothermic reaction, right? The reaction lost heat, but the heat produced is positive. The heat that is experienced by the environment will be a positive value. Okay, let's look at number 26. If you haven't done that yet, please pause the video now and do that. Okay, so this one is asking for how much heat is produced from burning rum. 1 liter bottle of rum, that is 40% ethanol. So when we combust ethanol, this is the amount of heat we have for 1 mole. So let's figure out how many moles of ethanol we're actually burning when we burn this bottle of rum. So how much ethanol do we have? We have 40%, or 40 over 100 times 1 liter of ethanol. But we need this in terms of number of moles, which we can convert to mass using the density, but first we need to convert to milliliters. There we go. And now we can convert to mass using the density, so 0.94 grams over milliliter. There we go. So now we have the density, the mass of ethanol. So number of moles of ethanol. We need to convert to number of moles by dividing by the molar mass. The molar mass of ethanol is 46.07 grams per mole. You plug all of this into your calculator, and we get a value of 8.2 moles of ethanol to 2 decimal places. Okay, so if we burn 1 mole of ethanol according to this equation, we get minus 1366.8 kilojoules for 1 mole. So we get minus 1366.8 kilojoules per mole of ethanol. But what happens when we burn 8.2 moles? Well, we multiply by 8.2 moles of ethanol, and what we end up with is going to be negative 1.1 by 10 to the 4 kilojoules of energy. So the amount of energy produced, right, would be 1.1 by 10 to the 4 kilojoules of energy. All right, so I know we talked a lot about, we've been doing lots of enthalpy calculations. In our next video, we're going to do even more enthalpy calculations when we look at standard enthalpy of formation. We'll see you in the next video. Bye.